Ladies and gentlemen, please welcome Jeff Kodosky.
Thank you. Good morning and welcome to day 2 of NI Week 2011. LabVIEW is 25 this year, so it's a perfect time to pause for reflection and to speculate on the next 25 years. LabVIEW has been on a successful trajectory since the beginning. I believe this success has been due to factors within the product itself and factors associated with the larger LabVIEW plus hardware I/O platform. On the product side, the core feature of graphical structured data flow programming has made programming automated measurement systems accessible to domain experts and indeed has inspired them to undertake and succeed at projects they normally would have considered too difficult or impractical to do. On the platform side, LabVIEW's comprehensive integration of analog and digital I/O and sophisticated platform timing capabilities have enabled domain experts to build complete high-performance measurement systems in a fraction of the time it takes with traditional tools. When we started out over 25 years ago, we sought to create a tool for scientists and engineers for automating measurements, a tool that would be as productive for them as a spreadsheet was for financial people. We weren't seeking to create a language, but that's what we ended up because we realized we needed that level of flexibility and control in order to deal with all the kinds of I/O and processing required. The language we created is a graphical structured data flow language, sometimes referred to as G, and it's the foundation upon which everything else is built. The integrity of this language has enabled us to continually expand the scope of LabVIEW while still preserving earlier investments. I think it's instructive to review the elements of this foundation, graphical structured data flow, to understand why it has supported all of the superstructure built on top of it over the years. First of all, when we talk about the language, what do we mean by structured? We mean that the language contains a small set of nesting control structures. As early as 1946, it was known and actually proved mathematically that sequence, selection, and iteration are sufficient to express any computable function. This was largely an abstract concept until Dijkstra argued in 1968 that all programs should be written in a structured form in order to make them comprehensible and maintainable and ultimately provably correct. The semantics of these structures are well understood, so these ought to be first-class elements in a language rather than constructed from more primitive elements like go-to statements. Okay, so that's structured, but where do we get graphical data flow? The historically accurate story is that the cool graphics capability of the Apple Macintosh inspired us to search for a way to exploit it for constructing programs. After experimenting with flowcharts, primitive data flow diagrams, state diagrams, other types of diagrams, and some ad hoc approaches, we finally settled on data flow once we had discovered how to make it structured. Putting the historically accurate story aside, let's pretend we are methodically deriving the solution we reached. Why choose data flow as the underlying language? From a big picture perspective, measurement and computation is all about data, so a methodology that focuses on what happens to data, where it comes from, how it's processed, and where it gets displayed seems to be a more natural way to express behavior. Turning the question around, we could ask why most of the traditional languages to date have been sequential control flow languages. The reason is because that's the way computers were designed to operate. Computers are sequential machines based on the von Neumann architecture, where instructions are fetched one at a time from a large uniform memory. Sequential control flow languages were an outgrowth of the computer architecture, and they're ubiquitous today. Until recently, this wasn't much of an issue, but with the explosive growth of multi-core machines and FPGAs, the situation has changed dramatically. More about that later. Most computer science students are so steeped in control flow languages that they come to think of just in those terms. But one only has to imagine driving a car in traffic or playing a team sport to realize just how unnatural sequential processing really is. Data flow, on the other hand, is a much more natural description. It can clearly and simply describe parallel activity. It isn't over-constrained by arbitrarily imposed sequencing, and it has a rigorous theoretical underpinning being closely related to functional languages. I would love to say we're amazingly prescient in our choice of data flow, that we foresaw the day when parallel processors and FPGAs would blossom and we wanted to be ready for it. But in reality, I'd have to chalk this up to inspired dumb luck. Our background in measurement systems probably caused us to value parallelism a little bit more than most practitioners, and so we went with our gut instinct that data flow would serve us well. Which leads naturally to the last feature of the core foundation, graphical. Depicting data flow programs is just simply impractical without graphics. Text is well suited to control flow programming because it's just as sequential as the programming methodology. But the parallelism in data flow requires a less constrained representation, 2D graphics at a minimum. A graphical representation clearly shows the parallelism, the connections and relationships, where data originates, how it's processed, and where it goes. Something else I've come to appreciate over the years is that a graphical representation also clearly illustrates program complexity. A corresponding text program is just as complex, but you can't see it. Not until you study all the variables and their relationships in the program can you tell just how complex the program really is. Underestimating complexity is particularly dangerous when you're trying to maintain a program. And many bugs are introduced into many programs by a seemingly benign change made by somebody who didn't appreciate the full complexity. There's another interesting point about the graphical representation of program structures. In a text language, a control structure is represented by a keyword and brackets to denote the start and end of the structure. A common cause of many software errors is misplaced brackets, confusing what's inside and outside the structure. In a graphical language, a structure has an elegant one-piece representation, a closed box. It isn't possible to have half a box, so there's no confusion about what's inside or what's outside. Here's an example I've thought about showing many times but never got around to it. Here's a typical text representation of a recipe, a simplified version of a recipe from Cooking for Engineers, which I tried, enjoyed, and highly recommend. The text looks small and compact, but you can't really tell anything about how easy or hard the recipe is until you completely read through it. So I felt for a long time that cooking would benefit greatly from a graphical recipe language. Here's an example, the data being the ingredients and intermediate results as they're combined and processed to produce the final dish. To me, it's much easier to grasp what's going on with the graphical representation. You can clearly see which things can happen in parallel, so if you have assistants, it's obvious what they can do without getting in the way. You can easily get an overview of what the recipe entails to see what steps constitute the longest path, so you can get an idea of the complexity and the time required. And in this case, you can clearly see the beer for the cook in parallel with preparation, so you know this is going to be good. I'm delighted by the Cooking for Engineers website because in addition to the typical text recipe, it has a stylized data flow representation as well. Check it out. There are two other core language elements that are important in the foundation of LabVIEW. One is hierarchy. It's well known and fairly obvious that hierarchy is necessary in order to scale to large programs. The interesting point, however, is that with data flow, the methodology is the same at all levels of the hierarchy, namely nodes connected by wires, and data flows the same way at all levels, and parallelism is expressed the same at all levels. Contrast this with typical sequential programming languages, where the syntax and the rules of composition are different at the different levels of statements, subroutines, programs, and scripts. And trying to achieve parallelism by introducing threads is a horrendously complex mess that impacts all levels. While the use of hierarchy in LabVIEW is not surprising, the uniformity of the hierarchy is a significant advantage. The last core language element is the built-in user interface. Because of our experience with instruments and automated systems composed of racks of instruments, we had an appreciation for the benefits of instrument front panels, not only for displaying status while running, but also for troubleshooting problems. When considering software as a hierarchy of modules, we saw the synergy between instrument front panels and the interface declaration of a module. Having a user interface built into each software module would provide a great place to specify the formal parameters and also visualize the actual values when the module is executed. We went so far as to call this user interface a front panel, and the software module a virtual instrument, the basis of the product name LabVIEW. An unexpected benefit that followed from this integral user interface was the ease with which interactive unit testing could be done. Furthermore, the whole process of incremental development is sped up greatly. An application can start running with very little implemented, a couple of controls on a panel and a couple of nodes on the diagram. Running an application early and often during development makes prototyping rapid and efficient, and completed applications can be ready in a fraction of the time compared to using traditional tools. In case you're relatively new to the LabVIEW community, here's my 2-minute history. Programming of LabVIEW began in the summer of 1985 with a skunkworks team that grew to 10 people. After 17 months of long hours, version 1 was released. October '86 also marks the birth of the random number strip chart demo, which still lives on. We quickly discovered that our intended customers were happy to continue using BASIC with their instruments, and instead a whole new group of customers came forward wanting to use LabVIEW in myriad ways we hadn't considered. To be successful in these new areas, LabVIEW had to scale up and greatly increase its runtime performance, so we immediately started development on version 2, which would have a compiler. While working on version 2, another opportunity presented itself. LabVIEW had been limited to dealing with box instruments at the end of a cable, but the language was really even better suited to direct control of physical I/O through A to Ds, D to As, and DIO ports. When Apple released the Mac II, an open Mac with slots, we were ready with a suite of DAC cards, and this was the beginning of real virtual instrumentation. The main goal of LabVIEW 2 was to have a high-performing compiler, but to be successful, we also had to improve the editing environment with things like wire stretching, multiple selection. And Apple introduced color monitors, so we had to figure out how best to support color. We had a terrible time trying to stop innovating and actually deliver something. Version 2 finally came out in January of 1990, and there were 57 magazine front cover stories announcing it. All this time, LabVIEW only ran on a Mac, and we really needed to get a version for the PC. Windows 3 finally made it possible to run a 32-bit app on a PC, so we were able to release the first Windows version in the summer of '92, and follow that with a fully multi-platform LabVIEW version 3 that ran on Mac, PC, and Sun workstations. That release also marked the first major additions to the language, including typedefs, units, occurrences, and globals. On a personal note, I've always been embarrassed by globals, particularly since I implemented them. I view them as necessary evils or pragmatic shortcuts, and I continue to hope that someday we will invent a better solution, something more structured, safer to use, easier to reason about, more consistent with data flow, and more easily distributed. In the mid-90s, the internet was expanding and growing in awareness and utility. We didn't know how it might evolve, but we figured LabVIEW ought to connect to it. So we created the Internet Toolkit in LabVIEW version 4. For 10 years, the most requested feature was undo. We finally figured out how to do it efficiently, and were able to release a multi-step undo in version 5. Also included in this version was the first multi-threaded execution engine, the VI server, and diff for graphically comparing VI panels and diagrams. Some of our early customers were convinced LabVIEW could and should be enhanced for real-time control applications. We've been thinking about this for a long time and eventually started a project to build an intelligent DAC card and a real-time version of LabVIEW that would run on it. LabVIEW Real-Time was released in 1999. Our PXI products were introduced in '97, and LabVIEW Real-Time quickly became the version of choice for our embedded controllers. We called the next version LabVIEW 6i as a cute way to emphasize the internet integration built into it. This was all the rage in the early 2000s, and marketing had a field day with that little I. This version was the first time we were able to show a VI panel in a browser. This was also the time when RoboLab began at Tufts University. It became the basis for our ongoing LEGO collaboration. LabVIEW 7 introduced Express VIs to simplify application development. Ever since LabVIEW 1, we had this dream to map diagrams to hardware, but didn't have a clue how to do it until FPGAs appeared. We released the first version of LabVIEW for FPGA along with our first FPGA-based DAC board in 2003. 2004 saw the release of LabVIEW 7.1 with a timed loop in RT and a single cycle loop for FPGA. This version also introduced a simulation diagram and a state diagram wizard, two new models of computation that could be well integrated into the LabVIEW language. LabVIEW 8 had the most new code in a single release. It introduced the project window, math script node, and shared variable, along with a generous supply of bugs, which we decided to remove in subsequent versions. LEGO Mindstorm's NXT was released in 2006. We created a simplified version of LabVIEW to program the NXT processor, and a couple years later, an even simpler version for the LEGO WeDo product. In the past few years, we've switched to a numbering scheme which makes our annual release cycle apparent. Recent releases have focused on multi-core support, support for wireless sensor nodes, integration of FPGA IP, real-time math script, the parallel for loop, compiler optimization, scripting, usability, and stability. And that brings us up to the present, where LabVIEW development is continuing at a faster pace with a larger team than ever before. Our investment in software R&D is unmatched in our industry. We're currently working on several long-term projects, research projects, as well as many near-term development projects to further advance technology we've already introduced. One area we are investing in heavily is an optimizing compiler. In the past few releases, we've introduced a new internal architecture for the LabVIEW compiler. This new infrastructure has enabled us to implement optimizing transforms during compilation to achieve higher performance and even more parallelism on multi-core processors. We have a similar effort going on for FPGAs, where we're developing high-level synthesis tools to generate more optimal code for FPGAs. Although it's more complicated because there's a lot more flexibility in trading off throughput, latency, accuracy, and resource utilization. One of the features of LabVIEW that has contributed a lot to its productivity is its fast compiler. For the most part, the compiler is invisible. Simply hit the run button, and a VI is compiled immediately and run. This makes it possible to rapidly iterate and incrementally develop an application. An optimizing compiler is in direct tension with this, since searching for and applying optimizing transforms is a time-consuming operation. Nevertheless, it should be possible to have more optimal code without having to sacrifice fast compile time. We're still brainstorming on these ideas, although we've already begun supporting FPGA cloud compiles since last year. In recent years, we've been dramatically expanding our platform capability in RF. Our advance into RF applications has highlighted the necessity for a simpler and more flexible means for specifying streaming computations, which are the basis for most communications applications. You got a glimpse of the DSP diagram in yesterday's keynote. We released the first version of Web UI Builder and are getting some great feedback on the most important directions for further development. I still see great potential in a zero-install environment for creating web user interfaces and connecting to general web services. The explosive growth of mobile devices and multi-touch interfaces is changing how we use computers, and we're excited about how we might exploit this technology in LabVIEW. We're exploring some radically new ideas that have the potential for enabling another leap in productivity in programming and design. And we'll show you some of that this morning. And I just have to say, it seems to me that this new technology makes text-based programming look even more outdated and irrelevant. During the first 25 years, LabVIEW has defined and delivered on the vision of virtual instrumentation. We've proven the benefits of graphical programming, demonstrating major productivity gains, and establishing the value of the virtual instrument as the fundamental building block of applications with its diagram and integral UI. During the next 25 years, LabVIEW will define and deliver on the vision of graphical system design, using interactive graphics and natural user interfaces to speed design, prototyping, and deployment of all kinds of measurement and control systems. Graphical system design is the natural evolution of our software-centric view of instrumentation. It steps out to the next level of integration to consider the entire system. Our goals really remain the same, however: deliver greatly increased productivity to help engineers and scientists accelerate their innovation and discovery. One of the engines accelerating innovation is the FPGA. I predict we'll see a convergence of multi-core and FPGA. New devices will consist of an extensive interconnect fabric with memory and computation elements liberally scattered throughout. These devices will be massively parallel. They will also have jettisoned the two foundational elements of von Neumann architecture: large uniform memory and sequential execution. so there'll be absolutely no rational reason to even consider programming them with sequential languages. Instead, LabVIEW, with its inherently parallel graphical structured data flow, will be the tool of choice. Another engine accelerating innovation is a new capability in LabVIEW we've been experimenting with and talking about for a while, which we refer to as the system diagram. From one perspective, you could say this is a graphical depiction of the project tree in LabVIEW, offering a much richer view of the relationship and interconnectivity of system components and a more natural interface for hardware configuration. But actually, the system diagram really represents the next level of abstraction in design, and we'll show you what we mean this morning. 25 years ago, I wouldn't have believed I would still be working on LabVIEW today. I knew there was a lot of potential, and I was fond of saying all along that I didn't see the limits of what could be done with LabVIEW. But I never imagined we would still be expanding LabVIEW's scope and application in 2011. Today, however, I'm just as excited about the potential, and I still don't see the limits of what could be done with LabVIEW. But now, I'm just hoping I live long enough to see what we can achieve in the next 25 years. If you'd like to get a glimpse of how it all started, there's a Mac Plus running version 1 in the LabVIEW zone on the Expo floor. In the About LabVIEW screen, we signed our work by including bitmap images of ourselves. See if you can recognize us now. Let's give a round of applause to the original LabVIEW 1 team for what they started 25 years ago. Thank you.